Hi everybody. Today I'm going to talk to you about simple harmonic oscillation. And if you think of the term, if you hear the term simple harmonic oscillation, you might be a little worried that it's going to be something pretty complicated. That phrase seems a little technical, and so I think it might help to break those terms down just a little bit, the words inside each, just so you see what we're dealing with here. So the first term is simple. Right? Simple should make you feel a little bit better because we're not talking about anything that's too complicated. You know that in this class we try to keep the math as simple as we possibly can so that we can really get at the concepts and let the math try to help us to get there. Second is this word harmonic. And harmonic should immediately bring up the idea of harmony in musical instruments. And so this is the kind of motion that we see oftentimes in parts of musical instruments. For example, strings or reeds have this kind of motion when they try to produce a musical note. The last is oscillation. And oscillation we've already talked about a few times, which is just a vibration around a rest position. If you put those three things together, though, simple harmonic oscillation, they mean something special. And I will tell you that oftentimes I will abbreviate it SHO just because I'm lazy. But if you put those two together, or those three together, what you should see is that we're talking about motion that is repeated, that is consistent. It doesn't lose energy to friction or air resistance or dampening or anything that we're going to be talking about over time here. It just continues to have this oscillation around a rest position without ever changing that motion, without ever losing any of that. So simple harmonic oscillation sounds technical, but it's really not too bad. So we've been dealing with springs here in the last few days, so I want to just kind of bring us back to that if I could. I have a mass, and I have a spring that's hanging from a support. So if I attach that mass to the spring, initially there's really not a lot of upward force when the spring is still compressed in its nearly rest position. When the spring is still compressed, it really doesn't pull up very much on the mass, but there's still this weight, and that weight is pulling down pretty hard. So if you look at it, you can see between the little blue vector and the big red vector that the red vector is going to win. And so as a result, we have a downward force, a net force in the downward direction that's going to pull the mass downward. And so we say there's this net force, and it's down. It doesn't really matter at this point how much that force is, just so you know that there is a net force downward. Anytime there's a net force, if you remember all the way back to Unit 2, a net force produces an acceleration. So this box, this mass, is going to accelerate downward towards a central position here, which we're going to talk about in just a second. Now, eventually, it's going to hit a place where the upward force from the spring and the downward force from weight are going to, or from gravity, are going to be balanced. And so what happens if there's no net force is that there's no acceleration at that point. So all the time here, it's been accelerating downward, but the upward force has been getting bigger and bigger and bigger, and so as a result, the acceleration downward has been getting smaller and smaller and smaller, until finally it hits the 0 point. Right here, we would call this a rest position. So I'm going to abbreviate that RP. RP is the rest position. At the rest position, the upward force for the spring, or the elastic force, and the downward force for gravity have balanced out, and so there's no acceleration at that place. But here it was accelerating and accelerating and accelerating until finally it got there, so we know that it should have motion. And so at this point, it may not have any net force, it may not have any acceleration, but it has motion. And because of its inertia, we know that it's going to move in a straight line at the same speed until a force tries to change that. That's Newton's first law, right? So it's moving downward, and so as a result, it's going to continue to move past this rest position because it has that inertia. Now what happens the moment it moves past that rest position is that the upward force continues to increase in size. And so the spring force, the spring pulls harder and harder and harder as the object is moving downward. And so the weight hasn't changed, right? The gravitational force hasn't changed, but the upward force has. And so if you look at the net force here, you're going to see that the net force is definitely in the upward direction at this point. So I'm going to go ahead and put F net equals upward. And I think you'll notice, especially because of the work that we've done in the last few days, is that the more you stretch it, the more there is an upward force. So as it continues to move downward, it's continuing to get a stronger force upward, which means it should have a higher net force upward, which means it should have a higher acceleration upward. And so it's going to slow down, slow down, slow down, slow down until finally it hits a point where it has no motion at that point. But at that point, it still has an upward force. And that upward force is because of the spring. And so it's going to start to move back upward again. It's going to start to accelerate back upward towards this rest position. So what we see is motion that goes from this upward position down to this position, down to this position, and then back to the middle, and then back upward, and then back to the middle, and then back downward again. And so you can see that that's an oscillation right there. And it's an oscillation around this place we call the rest position, where there's no net force. So that's how I'm going to define the rest position, is the place where there's no net force acting on the object. So it oscillates back and forth around that rest position. The reason that it does that is because of inertia. So you can see why we have to do this after we did forces and inertia, because we want to make sure to understand why it continues to move if there's no net force acting on it at that time. Now what's cool is if you go ahead and block this out here, so here we continue the pattern, if you will, you're going to see, I drew my spring backwards there, sorry, you're going to see it looks like this, and then over here it should look like this, like so. So if you connect those together, you can see that we have a pattern that looks like that. Over time, you can see we have that wave pattern. And so this is what we're using as our introduction to waves. But it's all based on the fact that there's this simple harmonic oscillation, that the particles themselves oscillate back and forth around a central rest position where there's no net force. But what happens in the process is we start with some potential energy, we go down and have only kinetic energy, and then we have only potential energy, and we continue that exchange back and forth. And in an ideal sense, in an ideal world, we don't lose anything, any of that mechanical energy to any dampening, any friction, any air resistance, or anything else. So it just continues to oscillate back and forth like that, and over time it will produce a wave pattern. These forces that keep it around that central position are called restoring forces. So it's trying to restore the position of the object at the rest position. It's trying to get it back to that place. But because of inertia, it never gets it to sit there. It always overshoots the mark. It always goes too far because it's giving it some motion in one direction or the other direction. The mass will never sit there. In the real world, we know that if we let a spring pendulum oscillate for a long enough period of time, the friction in the spring and the air resistance that the mass encounters will sooner or later take away all of that energy and make it into thermal energy, which is not useful for the motion of the mass. It's not mechanical energy anymore. It's a useless thermal energy. So it does rob it in the real world of that motion. But for us, when we're talking about simple harmonic oscillation, we assume ideal conditions for that. And this goes for an oscillating pendulum, so a pendulum that works like this, as well as a spring pendulum. If we mounted the spring horizontally and had it on a cart that was oscillating back and forth, that would work too. Anytime you have restoring forces that are trying to get an object to move back to a rest position, so a position where there's no net force, you're going to have, or you could have, simple harmonic oscillation. So that's our goal for the rest of the week, is to talk about simple harmonic oscillation and do a lab that goes with it using a pendulum. Not this kind of a pendulum, but an actual rotating pendulum. A simple pendulum is what they call it. Hopefully that makes sense. If you have any questions, let me know.